Hi, welcome to today's session. So today we are going to discuss about the latest trends in software architecture. So today we are specifically going to talk about that how well that your software can absorb changes. You know, in today's day and age, the software tend to change very rapidly. The customer requirements are getting demanding, and customers are requesting a lot of changes day in day out. So we'll see how we can design a software in a way that we can absorb these changes in a quick succession or in very rapid way. So first of all, let's discuss that how we design our software or develop our software. So first of all, we get our preliminary requirements from our customer, and then we do our software design and architecture. So based on this software design and architecture, we develop the version 1 or version beta, alpha, whatever the name that you are giving into it. And then we deploy or deliver this software or the first version to our customer. And then customer is analyzing this software and they are giving their feedback to us. And we are incorporating these feedbacks or the customer feedback into software and develop the subsequent version. So you know, in today's day and age, this particular cycle is going on and on forever. And if you compare this thing with a little bit of an older software development life cycles, you know, this to go to this, to execute this particular cycle, it takes a bit of time, maybe like doing the releases once every like 3 months or 6 months time and all that, especially that when we are using software development methodologies such as waterfall. But now things have changed a lot. There are certain companies who are doing or delivering their latest versions to the customers 100 times per day. If I name something like Netflix, Uber, eBay, so these guys are like doing very rapid deployments with continuous integration and continuous delivery. So let's see how we can deliver such software in a rapid way and absorb those changes into our software without failing our existing functionality as well. High velocity is one of the key aspect or key feature in the modern day software industry. So now we are going to see how we can deliver or how do we deliver normally these software products. So normally we do have experiments that runs on for weeks. So if you are practicing agile, so this one is more or less like a sprint. And within a sprint or within an experiment, you have stories which runs for several days, and these stories consisting of several tasks which we can or developers or engineers can finish off within few hours. So that is how our normal delivery mechanism is formed up. So what are the things that we can do to enhance or speed up this overall delivery process? So we can start with the code itself. We can do the code analysis by using tools such as SonarQube. So SonarQube, you can automate this source code analysis to analyze your source code in terms of security and in terms of source code quality as well. So you can automate these tools or automate this process using these tools by using CI/CD pipeline. And you can use unit testing. So unit testing ensures that whenever that you do change to existing functionality, your code or your expected outcome won't break. And the build and automation. So as I told you earlier, we can use CI/CD tools, continuous integration and continuous deployment. So we can use CI/CD tools along with the containerized mechanisms as well, such as Docker. And we can use test automation as well. So as you know that in today's day and age, we are not using the manual QA process or quality assurance process for softwares anymore, because it takes time because there's human involvement. So because of that, we need to do a test automation. Whenever that there's a build going on, there should be automated scripts for QA, and those scripts should run and make sure that the required functionality is there. And then we can use the container management tools or container orchestration tools such as Kubernetes, Docker, Swarm and whatnot, everything. So all these things lead into one thing. If you are familiar with these buzzwords, you might have heard about this term before, the microservices. So all these things are lead into microservices. So I'm not going to explain what are the microservices and go in depth about microservices here. But let's see what are the advantages that we are having using microservices. Microservices are independently deployable artifacts, and you can have, if you have a geographically separated teams, so this would add a lot of value during the development process as well, and it improves the fault isolation, and it is technology agnostic as well, and it increases resiliency, and there are many more advantages of using microservices or microservices architecture. So can we like overcome all our problems using microservices? Because if you are go to a software architecture conference or software conference generally, that everybody is talking about microservices, but we need to analyze and see that whether it's a kind of like silver bullet for all our problems, and of course it is not. So what are the problems that are coming with microservices? So inherently microservice is a very complex architecture pattern, because microservices, if you do it correctly, it's a distributed architecture pattern. So all the distributed architecture patterns are inherently complex, and we need to do monitoring and discovery as well. Like if you go ahead with microservice without proper monitoring and discovery tools, that it's almost like you are going in the dark. And I mean, if you do not use microservices properly with the correct architecture patterns and all, then it will lead up into low performance. You may be trying to go migrate into microservices architecture to enhance your performance, but you will be end up with less performance than your existing monolith. Because whenever that I'm doing consultation, I have seen a lot of people are misusing microservices principles, and they hit up with a lot of low performance, or they end up with a lot of low performance systems. So mainly because of a lot of unwanted internal service calls or internal service hops. And this microservice architecture is better suited for large organizations. Let me explain you why. When you are talking about the team size of a microservice, we are talking about around like 3 to 4 people who are developing the microservice, who deploy in them, and who maintain those microservices as well. So if you are talking about around 100 or 200 microservices, so we are talking about around like 800 or 1000 odd engineers. So if you are a small company, I mean, of course that you do not have that much of engineers, where one set of team is maintaining or developing and maintaining one particular microservice. So that is another fact. I mean, if you are talking about companies like Netflix, Amazon, Uber and all, they have like large pool of engineers, so they can easily adapt into this microservice. Another one is the lack of technical knowledge and dependency management. So there are a lot of like issues regarding these microservices. So, and now let's see what we can do about it. So I think you are a bit familiar with this notation. This one is called the big ball of mud. So what happened to most of the architectures is that they started with the big ball of mud, like they have like ever growing monolith, so then eventually it becomes a big ball of mud. So that is the notation that we are giving to like very complex monolith which tangles everything together. And then companies started to migrate to microservices, and they end up with something called a Death Star. So Death Star is something like this. So like I mean, these are the real architecture diagrams in Netflix and Amazon. So you can see everything is connected to everywhere, and it becomes like very strangled ecosystem. So in order to manage this kind of system, that you have to have like huge team. Otherwise if one thing fails, it's very like harder to determine where it get failed and all. So that's what I told you, that monitoring, tracing and all these things are very important if you are maintaining a Death Star like this. So let's see what we can do about this now. So let's see what we can do about this big ball of muds and Death Stars. So then again, does this means that this big ball of mud or Death Stars are bad? I mean, we cannot say that. That is any particular company's choice. I mean, like if you have a monolith and very legacy monolith, if you still, I mean, if that particular monolith still serves your purpose, your user requirements and all, it is okay to have a big ball of mud. I mean, like you will be having some issues of like updating existing functionality or introducing new functionality, then you might be having some problems, but still it works. And that size also same. I mean, like if you, I think most of you guys are watching Netflix, but you are the underneath architecture supporting all the Netflix architecture is a Death Star, but still it works. So that depends on the on your requirement and how your company grows over the time. So let's focus on how to get rid of these things and how we can incorporate microservices and later software trends in a fairly small organization. The, the first architecture pattern that we are going to analyze here is called the domain-oriented microservices, or DOMA. So what do you mean by this? So as I told you earlier, the microservice architecture pattern is inherently suitable for fairly large organizations. But what if that you are a fairly small organization and still want to do microservices? So what you can do is you can segregate your services into a certain domain, and you can use technologies such as or techniques such as domain driven design to identify and segregate these domains. Within this domain, you would be having lot of microservices which are doing independent responsibilities, or which are serving independent responsibilities. So one particular team can take care of this one particular domain. So you don't have to have a team per microservices, but you can have team per domain. And you can have a generic API gateway or a message queue hub where you can communicate with other teams. So you can have that separation or the domain separation using API gateway or a message queue. So using domain oriented microservices, you can still get the advantages of microservices architecture within your small organization structure as well. In this domain oriented microservice architecture, as I told you earlier, we can enable the communication in between one domain and another domain using a message queue. So why we have to use a message queue here? Can't we use just an API call or some other RPC call or some other mechanism? Of course we can, but using a message queue, and if you are using a proper message queue such as Kafka and all, then we can enable something else, which is the event-driven architecture. So if your messaging protocol supports event-driven protocols, so then you can implement an event-driven architecture and communicate in between one domain and another domain. And of course, you can implement this kind of an event-driven architecture within your domain as well. Of course, that is possible. But what are the advantages that we are having when we are implementing event-driven architectures, especially in between domains? So the most important aspect is the reduce of coupling. So you know that the basic principle is that you have to reduce the coupling and improve the cohesion. So if you can reduce the coupling by using an event-driven architecture, so that would be a huge benefit in between domains and in between microservices as well, if you can. And you can use a technology such as event storming, actually not a technology, a methodology such as event storming during the design stages. You can Google this and find out how to do event storming and how to actually implement event-driven architecture as well. I'm not going to explain detail about event-driven architecture here. And you can use event sourcing to persist your events in a chronological order. So then if you want, you can replay the events and create the scenario back again. And this event-driven architecture pattern helps you to handle heavy data loads as well, because you can scale horizontally in between your microservices or in between your domains based on the data load which is receiving to your event bus. So those are the advantages of using event-driven architecture. So if you are using, or if you are trying to architect a data-driven or data-intensive platform, event-driven architecture is a very good choice. We talked about a distributed architecture pattern here, which is event-driven. So whenever that when it comes to an is distributed architecture pattern, we have to determine how we manage our services. So either we need to use choreography or orchestration. If not, all these services that we are trying to spin up in our microservice architecture would go as headless chicken. I mean, we cannot afford to do that. There should be some kind of a mechanism where we can manage. So if you know that what you are trying to do in between your microservices or in between your domains, and if you can catch all the exceptions or execution branches with all the fail scenarios, then you can use choreography. So if you are not 100% sure about all the fail scenarios and all the exceptions that you can catch, then it is better to go with orchestration. Actually, this talking about whether to use choreography orchestration is a totally entire different we have to have a different discussion to determine whether we are using choreography or orchestration, but you have to use either one of these things. And if you are using orchestration, you can use orchestration tools such as Netflix Conductor, Camunda BPN, or Cadence or Temporal in Uber. So these are the orchestration tools that you can use to manage your microservices. And you can use patterns such as Saga pattern, or some people are using two-page commits as well, to make sure that the atomicity or the commit atomicity in between services. Serverless architecture is also a very good pattern when it comes to modern architecture patterns and distributed computing as well, because the advantage is that if you are, as I told you earlier, if you are using heavy data loads or data intensive application, and if you want to spin up a lot of services based on your number of requests or number of data load, then it's better to go ahead with serverless, because in that case you are paying only for what you are using. I mean, like, what you're talking about here is horizontal scaling. So whenever that there are a lot of instances that you need to spin up, then you can spin up these services using serverless computing based on the demand. So but if you're going in the other way around, I mean, you might be like you are keeping persistently EC2 services or Azure VMs, and you are paying for these VMs or persistent entities whether you are using it or not. Another architecture pattern that you can use in distributed computing is called CPQ or Command Publish Consumer Query. I think you are familiar with CQRS, which is Command Query Responsibility Segregation. So that is in CQRS, what you are doing is just like you are reading and writing data into two clusters. But Command Publish Consumer Query is little bit different than that. So what does it do is it is publishing it is publishing the commands which is receiving to a DB, or it can be a message broker, or it can be, or this DB can be perceived as an event source or a message broker, and it just publish those events into an event hub. So the communication in between two microservices or two domains can be arranged using an event hub. So in the receiving end as well, the receiving service or the receiving service domain consume these events, and it is executing the query. So this is called the command publish consume query. So this one is very popularized with the serverless architecture as well. So you can like I'm just giving you the very high level details about these principles here, and you can Google it and find it out, these architecture patterns in detail. And the other important aspect in distributed computing or modern architecture per se is called micro frontends. So I think, people have worked with the backend backend segregation of services using event-driven architecture or microservices or whatnot, everything. But we used to have like good old monolith as the front end, whether it's an Angular application or React application or simple ASP application, because all these things are like technically monoliths. But around like 2 years ago, people have tried to segregate the front ends as well based on their domains. So in here, as I depict in this example or in this picture, what we are doing is like we have like different front ends here, and they have their own build and test pipelines, and they can push into the production environment independently as well. And we have like such frameworks such as single SPA where we can utilize to build this kind of micro front ends. We are enabling all these features to rapidly deploy our changes into the production quickly. So that's why that we are using event-driven architecture, microservices architecture, micro front ends, and whatnot, everything that we have discussed so far. So all these things are leading into one thing, that is the evolutionary architecture. So as a software profession, our industry is changing very rapidly. So our softwares are changing very rapidly. So how we can make sure that whenever that we are doing change anything, or we are doing these rapid changes into our products or systems, how we can make sure that it is intact or it is not breaking apart. So the most important thing in here is called the architectural fitness functions. So architectural fitness functions means that you are defining some kind of parameters uh, during the design phase, and come into some kind of an agreement and saying that okay, these parameters would not change despite the fact that any feature or any functionality getting changed. So how you can measure these fitness functions? So there are a lot of matrices that you can use. Actually, I'll be doing a totally different video about this evolution architecture and fitness functions. But for the time being, we have to have matrices, we have to have monitors, and unit test plays a major role, chaos engineering, and there are many other things where you can use as architecture fitness functions. We are using a lot of automation, so automation pipelines when we are developing and deploying into our production environments. So let's see how we can use the fitness function in these pipelines. So you can see it in here that I have implemented a fitness function in here. So these fitness functions can define, as I told you, using many matrices, monitoring tools, and whatnot, everything. So you can define you can define in terms of like performance wise fitness functions, security fitness functions, functional fitness functions, and a lot of things. So then you can integrate these fitness functions into these pipelines. So whenever that you are doing a build pipeline, so it runs all these automated scripts and ensures that none of the fitness functions are failing. So that means that your product is good to go into the production. After the UAT stage, you can define few holistic fitness functions as well before you do the integration. So before you push these things into the integrated environment. So there are a lot of things that you can do in this way. So what are the, as I told you, so these are things that we can check using our fitness functions: the code style quality check, the unit test, the static code analysis, automated API load and performance test, dynamic analysis, container compliance is very essential in these days, because most of the nowadays softwares are shipping into the production environments using containers, and we have to be very precise on security as well, and we need to make sure that none of the binaries or the container images are getting affected by malware or any other anomalies. So by using fitness functions, you can ensure all these things are in correct order. Now apart from these, let's see what are the other latest trends that we need to consider when we are designing our new software. So these are the few like I would say some buzzwords in these days. The AI and ML, because like most of the systems are getting powered with AI and ML, because now like we would, it's like more or less that we are going away from bit of like deterministic programming into more or less like fuzzy programming these days with AI and ML. And there are a lot of other advantages that you can use AI and ML as well, is that we have like lots of data sets that we can work with. So AI and ML would play a major role in most of our software applications in near future. So we need to consider these things when we are designing or architecting our software applications. And edge computing is also like picking up, because like the most of the end device or leaf machines are getting leaf machines, say that the machines that are used by people at the end of the chain are getting very powerful. So you can do a lot of computation in these machines itself as well, comparing to earlier, like server oriented architectures. So that thing is also like you need to consider. And blockchain is also getting like picking up, because whenever that we are talking about integrity, the data integrity, the data authenticity and all, blockchain is also playing a huge role. And data incentive computing that we have talked about a little bit earlier as well, and rapid application development or low code to no code also playing a huge role, because like customers cannot wait these days. I mean, they need their softwares to be get built by tomorrow. So LCNC is also playing a huge role in near future. And the other thing is the hybrid cloud. So that most of the people are still sticking into one cloud vendor, as in AWS, Azure, or GCP. But the thing is that there are certain things that Azure is doing well comparing to AWS and GCP, and in some parts GCP is doing some specific features better than other cloud providers. So hybrid cloud or the poly cloud would also become very popular pretty soon. So people would deploy their applications across many cloud platforms. Multiple data stores also would play a major role, because earlier what we used to have was like just a central RDBMS or relational database. But now we have like these S3 buckets, document databases, key databases, and whatnot, everything. So multiple data stores is also another fact that you need to consider when you are developing or designing your future software applications. And real-time data streams, like this is also a very huge thing now, because we have like a lot of big data coming up with many sensors and many other sensory nodes and all. So we need to like most of the applications that we are working with these days can or needs to support real-time data streams or big data streams. And finally, the most important thing that would come in pretty near future is quantum computing, because when it comes to the quantum computing, most of the paradigms that we used to have right now would change, from security itself, from cryptography to many other aspects would get changed. So it is essential that you would be having some understanding in quantum computing as well, because in another like 6 to 7 years, most probably we would be using quantum computing to in our day-to-day lives. So this is just kind of like prediction. I might go wrong, but that is also some kind of a thing that we can consider when we are designing our applications in future, not near future, I would say in 5 to 6 years time. So that concludes today's video. So these are the few books that I referred in this lecture or in this video. So if you are also interested in to study more about these things, you can refer these books as well. Thanks.